Yes, welcome back, dear students. Uh, today we're going to discuss the second chapter of Module 3, which is based on the core components of an embedded system, or core in general, the core of embedded systems. Previous class you understood that is in chapter 1 of Module 3. The introduction to the embedded system, you understood most of the basic things there. Uh, now we are going to discuss the core components that are used in the embedded system. And again, when I say core, it's ultimately the brain of the embedded system, or the processor, which is used inside the embedded system. You can use the microprocessor or microcontroller, and even there are a few more other processors which you can use inside the embedded system, like the digital signal processor, the special processor which is used for processing the multimedia data like audio, video, all these things. Especially DSP, digital signal processor, is used in the embedded systems which are developed in order to deal with the multimedia data like audio and video. And similarly, we are going to discuss the other core components which can be used inside the embedded system, like application specific integrated circuits, application specific standard uh, uh, application specific standard processor, and then the cards commercially off the shelf systems, and these are few of the systems, core components of the embedded systems that we are going to discuss in the today's class. Just as the agenda, that the first thing that we discuss here is the core of the embedded system. What are the core components that you can use inside the embedded system, or the core brain components of the embedded system? That is what we understand, and after that we understand the memory, sensors which access the inputs to the embedded system, actuators which are connected to the output ports of the embedded system and which act as basically the output devices to the embedded system, and the communication interface, how to make the embedded system communicate with the rest of the world, or with the external world. And we are going to discuss on the embedded firmware, the permanent software which is permanently stored inside the root only memory. And we also discuss not only the core component of the embedded system, we also discuss the other components which are found inside the embedded system. Now we are not going to discuss all these things inside in the today's class itself. Today's class we are going to focus on the core of the embedded system, and later on in my other classes we are going to discuss these things from 2.2 to 2.6. Now this class we focus more on 2.1, that is the core of the embedded system. Now the learning objectives of this chapter, you're going to learn about the building blocks of the typical embedded system. What are the major building blocks of the embedded system? You cannot assume an embedded system without the core, and the focus is more on the core of the embedded system in the today's class. Now, in general, when I say core, this all these things are the cores. Inside an embedded system, you can use a general purpose processor, which is abbreviated as GPP, general purpose processor, and then application specific instruction set processor. This is what I was telling, the processor which is designed in order to perform the execution of a specific application. And then the microprocessor, microcontroller, and this is what I told, the digital signal processor. And again you can have the CISC processor and the RISC processor, and two types of architecture. This also we understand. So I've already told you on Harvard and VARD it is, R is missing, Harvard and one human processor architecture. When in the previous class, I have already told you about the Harvard and one human processor. So all the CISC processors are based on the one human architecture, and the RISC processor are based on the Harvard architecture. If I take a ARM microcontroller, it is a combination of these two. Now, when I say one human processor, you have a single memory which is holding both data and instruction. When I say Harvard architecture, it has a split memory, separate memory for holding holding the data, and separate memory for holding the instruction or the program. And of course, the separate paths are also there, separate data path and separate instruction path in the Harvard processor. Now, one human processor, there is a single unified memory which is holding both the data and instruction, and hence a single path for both data and instruction. And later we are going to discuss about the byte orderness. There are two Indianness, which basically deals with the byte ordering. One is big Indian byte ordering, and another one is a little Indian byte ordering. And you know little about the big Indian and little Indian byte ordering techniques. We are going to discuss the differences between these two with the examples, and later we understand the load store operations and instruction pipeline. And basically this ARM processor is a load and store architecture. Our instruction set of the ARM processor comes under the category of load and store architecture. So I've already told you that there are two architecture. One is register memory architecture, and another one is a load and store architecture. ARM basically comes under the load and store architecture because the operations which you can do on using the ARM instruction set, both the operands must be inside the register. That means you cannot perform the operations if the one operand is in register and another operand directly in the memory. You got to get both the operands to the registers, and then you can perform the operation. Now, if I say register memory class of architecture, so those architecture, they allow the operations to be performed even if the operands are available in the memory. One operand in the register, another operand in the memory, you can perform the operations. But when I say load and store architecture, the operations are performed only on the registers. So for that reason, it is necessary for you to get the operands which are there in the memory to the register, and then you can perform any data processing operation. So that is what we look here. And we also learn about the different PLDs, that is programmable logic devices. So there's last class also I have mentioned when I was explaining, I told about the programmable logic device. These are the devices which have the large number of gates. Say for example, and gate a plane and OR gate plane, or basically it is the planes of the basic gates using which you can reconfigure this programmable logic device to perform variety of functions. And we're going to discuss more about this programmable logic device later. That means when I say the core of an embedded system, even PLDs can also be the core of the embedded system. And again, there are two types of PLDs. One is complex programmable logic devices, and another one is a short form, it's called as CPLDs, and another one is field programmable gate arrays, called as FPGAs. So we are going to discuss these two later in detail. Now this PLDs can also be the core of an embedded system. Now what you're going to learn about the different memory technologies and memory types used in the embedded system development. What kind of memory, ROM, PROM, programmable read-only memory, OTP, one-time programmable memory. So that is, the memory can be programmed only one time. EPROM, erasable programmable read-only memory, EEPROM, that is electrically erasable programmable read-only memory, flash memory. So these are all the different types of memories which are used for storing the firmware inside the embedded system. And then you also understand the various other RAM, random access memory, that is SRAM. Some of these we have already understood in the previous classes, that is serial access memory, then static RAM, and then dynamic RAM. Now, and few differences between static RAM and dynamic RAM I have already told you in the previous session. Dynamic RAM, it requires the constant refreshing. The memory cells need to be refreshed periodically. That is in the range of microseconds. They need to be recharged, refreshed. And then non-volatile SRAM. These are a few different types of memory systems that we'll be discussing later. That is when we go to the section 2.2. There we will be focusing on these things. And one more important thing that you understand is the different factor that needs to be considered in selection of memory for embedded system. We have these many types of read-only memories and these many types of random access memories. Now, which memory to choose? So, what are the different factors or the parameters I should look in order to select the read-only memory and the random access memory? So that is what you'll be learning in this chapter. And then you understand the role of the sensors, actuators, and their interfacing with I/O subsystem of an embedded system. So as I already told, sensors are always connected to the input ports of the embedded system, and actuators are always connected to the output ports of the embedded system. Sensor senses the input data and gives it to the embedded system. Embedded system processes the data, manipulates the data, and conveys, produces the output of the embedded output to the users through the actuators. So and you're going to discuss more about the sensors and the actuators in this chapter. And later we learn about the interfacing of LED light emitting diodes. How do I interface an light emitting diode with the core of the embedded system? And then how do I interface a 7-segment LED display? I think you know 7-segment display. In the previous semester you learned LEDs also, and you'll also understand how to interface a buzzer. It's a sound emitting device. How to interface a buzzer to the embedded system, how to interface a stepper motor, how to interface a relays, how to interface a keyboard. We are going to discuss in this chapter how to interface a small a keyboard, a 4x4 keyboard, how to operate interface a switch button, push button switches. The push button switches, one single button which is used to perform the multiple operations. Now, say for example, the garage door opener. Now I want to open the door, I want to close the door. I don't require two push button switches for performing these operations. I can manage everything using one push button switch. And this push button switch operates by examining the current state of the mission. Say for example, if I consider the garage door opener as the mission, and I have one push button switch. Now if currently the garage door is closed, and if I push this button, the door will start opening, and when the door is in the open state, and if I press the same button again, it will start closing. So now this push button understand what is the current state of the door, and then behaves accordingly. It takes the system to the next state based on its current state. And similarly, if assume I press the button and the garage door is closing now, and it is half closed, and I press the button again, it will start opening again. And similarly, assume the garage door is in the opening state, it is half opened and it is not fully opened yet, and immediately if I press the button again, the same button, the garage door will start closing. Now and then this is the example. Later you're going to understand how to interface a simple push button switch with the embedded system. And then programmable interface device 8255, and this was used earlier. Your seniors used to use 8255 in order to interface all these things: the stepper motor, LED, 7-segment display, keyboard, push button with the microprocessor. Now we don't require this 8255 because the ARM microcontroller itself has a majority of the peripheral devices, and it has the output ports, input ports and output ports, using which I can connect the sensors and the required actuators. So 8255 is a programmable interface device which was used to interface all these devices with the microprocessor 8086. So this was used as an interface device. Now since we're dealing with the ARM microcontroller, now 8255 is not required. It's called as Programmable Peripheral Interface Device. PPI is Programmable Peripheral Interface Device. So 8255 again basically it had 3 ports, port A, port B and port C, and each capacity of each port was 8-bit. So I think that we need not go much detail on 8255 because this is not in our syllabus now. And we're going to learning different communication interfaces for the embedded system. How do we interface an embedded system with the external world? We understand next the various chip level communication interfaces like this. I2C, there is a bus called as I2C, and then there is a serial peripheral interconnect bus, and UART, universal asynchronous receiver and transmitter bus, one wire parallel bus. All these communication interfaces we are going to discuss at the later point of time. And then we understand the different wired and wireless external communication. These are the examples for the wired communication. RS-232 cable, RS-485 cable, parallel port, USB, universal serial bus, all these things. And for wireless communication, we understand all these things: Bluetooth, Wi-Fi, Zigbee, GPRS. Now, yeah, and then know what embedded firmware is and the role in embedded system. And finally, we are going to discuss what is the major role of the embedded firmware, the software which is permanently stored inside the RAM, and what it is going to do. All those things we understand. And one more thing that we understand is use different components, like reset circuit. Embedded system, there will be a reset circuit. Any point of time, if something happens, if the system hangs, you can use this reset circuit to reboot the system. And the embedded system will be having an internal brownout protection circuit. Now, and majority of the embedded system will carry this brownout protection circuit. Now, what is this brownout protection circuit? Now, if the voltage level for the embedded system goes below goes below the required operating voltage level, then this brownout protection circuit will automatically reset or reboot the embedded system. This circuit is basically protecting the embedded system from the damage. Now, what brownout protection circuit will do is it will automatically go for rebooting or resetting the embedded system in case the voltage level goes below the required operating voltage level. Now, and then oscillator circuit will understand, because either the microprocessor or the microcontroller, if it wants to do any operation, it requires the clock cycles are required, and all clock cycles for the processor, the microcontrollers, are supplied from the oscillator circuit. And then real-time clock. This is one more, because if you want the embedded system to perform certain operations periodically, so we make use of this real-time clock. And then the watch dot timers also can be used for performing some of the tasks periodically at regular interval of time. So these are a few things that we'll be understanding, but it's not possible in the today's sessions to cover all of them. Now, what we understand in the today's session is the core of the embedded system. What are the components that can be used as the core of the embedded system? Now, so typical embedded system. An embedded system contains a single chip controller which acts as the master brain of the system. So it's a single chip controller, and this basically is the brain of the embedded system. Now, what can be the master brain of the embedded system? So the master brain of the embedded system can be a microprocessor, or you can use a microcontroller. And the previous slide I showed you, you can also use FPGA, the field programmable gate arrays, which is a type of PLD, that is programmable logic device, which contains a number of logic gates planes, using which you can reconfigure the device in order to perform any type of function. So now when I say the master of the embedded system, or master brain of the embedded system, it can be a microprocessor or a microcontroller, or even sometimes it can also be a what FPGA, field programmable gate arrays. We'll be discussing more on this later. Or it can be a digital signal processor. This is what I was saying. If the embedded system is designed or designated for processing the multimedia data, then it will definitely carry the digital signal processor. Or the master brain of an embedded system can also be an application specific integrated circuit or application specific standard product. So there is a slight difference between these two, I'll tell you. Now, application specific integrated circuit is a proprietary product, whereas application specific standard product is not a proprietary product. It can be sold in the open market to anybody, but this cannot be sold in the open market because these are the integrated circuits which are developed for a specific customer, and they hold the right on this integrated circuit, and these things cannot be sold in the open market. It is a proprietary product, whereas application specific standard product is a non-proprietary product which can be sold in the open market. This is the only difference between these two. Now you understood what can be the master brain of an embedded system. So master brain of an embedded system can be any one of these things. And later, an embedded system also has a software system, which is and this software system is basically designed in order to regulate the physical variable or to manipulate the state of some devices or state of some variables by sending some control signal to the actuators or devices connect to the output port of the system. Now the embedded software system basically performs this. It regulates or it monitors the physical variable or the input variable and manipulates according to the control logic or the control algorithm that is written, and also sends the control signals to the actuator connected to the output port of the system. That is what basically the embedded software system does. Now here is a simple diagram using which you can understand. See the brain, there's the human brain I've shown here, which performs this task. What task? Just regulate, monitoring the variable and then manipulating and then sending some control signals based on the manipulation what it has made to the actuators or the devices connected to the output ports of the system. Now that is what the brain, and the brain, as all this sense organs, you can see, you can hear, you have the actuators, and so these are some of the sensing devices which can be used as input to the brain. You touch something, the brain immediately senses it, here, and it goes to the brain and it processes. When you see something, so it goes to the brain and it can process. And similarly the actuator, these are the sensors, and again actuators, the hand is in both the side, so it is here also, correct, right? The sensors, and it is at the actuator also. If brain after processing something, it sends some signal, the hand does the task accordingly, and when the brain processes something and I want to convey something to the other user, it is through the speech, and of course it's only for the input. Next, now these are the organs. This is the human, and similarly when it comes to the mission, this is how it happens. I have these many devices acting as the input devices, keyboard. I can give input to my system through keyboard, through mouse, the gamepad, joystick, and the microphone. Through microphone I can give the voice input, to the system, and the input goes, and here we have the kernel space, which has the access to majority of the routines that are residing inside the kernel, and the middleware, and there's a loop. This whole thing is a software, which takes the input, and with the help of the routines which are present inside the kernel, the processing happens, and finally the kernel, and you have a small piece of application written on top of this kernel, which monitors the how the computation is happening, and finally the kernel produces the output, and the output is displayed in the TFT monitor like this, or the CRT monitor, or the TFT monitor, or even it could be a small LCD display panel also, and the speakers are the headphones and the gamepad again. So this is how it happens. So now you this small slide, this slide gives you an analogy between the human brain, sensors, and the activators with that of the hardware and software components in the embedded system or the computer system. Now, what are the input devices to an embedded system? Input devices to the embedded systems can be the keyboard, push button switches, as I already told, so push button switches, these are all the inputs. From the keyboard I can key in something, and from the push button, as I already explained with the example of what garage door opener, one single push button in order to control many states of the machine. Now one single push button for the garage door opener, you can close the door, you can open the door. If the door is on opening state, you can push it back to the closing state. If the door is in the closing state, you can push it back to the opening state. Now you have one single push button doing all these tasks. Those can be the input devices. And similarly, what are the output devices for a typical embedded system? For a typical embedded system, the output devices can be LED. You can have the LCD displays, and even electric buzzers can also be the output devices for the embedded system. And there's a few examples which are listed here, but you can have plenty of those input devices and the output devices